Welcome to all. Today my topic is variant of Turing machine. So before going to that topic, first you know the aim of the what is the aim of the session. The aim of the Turing machine, if the aim of the section is to describe the Turing machine, and the studying the variant of Turing machines is to extend that understand the computational theory beyond the classical Turing machine model. So here we our basic aim is we describe various type of Turing machine. So what are the instructional objective of this? So the instructional objective of this session is understanding Turing machine variants, analyze computational power, apply the theoretical concept. So here in the instructional objective says that we are describe the various type of Turing machine and understand what is the difference between the basic Turing machine and the different type of Turing machine, and we also compare the computational power of the different Turing machine with the basic Turing machine. Also apply the theoretical concept. Next, after that, the outcomes of this topic is student will know what different type of Turing machines and its variants, and evaluate the computational efficiency and apply the theoretical concept and also theoretical analysis. So there are many variants, but we are here describes three variants. One is the multi-track Turing machine, multi-tape Turing machine, and third is the non-deterministic Turing machine. But here only three we can discuss. First we go for multi-track Turing machine. Basically all of you know that the Turing machine has the tape like that. Tape is like that, and there is a read write head, and this is the infinite blanks are there, and the symbol is written in the symbol is present in the whatever symbols are present in the head. Head is pointing to the first symbol and it is moving left to right. So it is only one tape with one track. This is the basic Turing machine. But in case of multi-track Turing machine, it has multiple track, means K track, and one head, only one head. It will be operate on the K track, and only single read write head. This head will be read the tape symbol and also write on the tape symbol. We also analyze the tape structure, head movement, and the computational power of the multi-track Turing machine with basic Turing machine. Basic Turing machine is the single track and single tape Turing machine, which is we can compare with the tape structure, head movement, and also computational power. Computational power means basically we analyze that or compare that what is the computational power. We compare using what language accepted by the basic Turing machine, and that language also accept or not by the multi-track Turing machine. A single track Turing machine has a single tape where the input is written and the machine can only read from and write with the single track. For example, here the single track Turing machine, and the read write head is here. If the symbol 1 is present here, then it reads the 1 and make it X, like that. Read write in the single track. Multi-track Turing machine means it has multiple track with single head and allowing the machine to read from and write to the multiple tracks simultaneously. Here single track Turing machine head can move left to right in the single tape or one cell at a time, like that. One cell at a time the head can move either left. Suppose head is here pointing here, either it can go to left or it can go to right. So but in the multi-track Turing machine, one head can write all the tracks simultaneously. Interestingly, the single track Turing machine has same power as multi-track Turing machine, because in the single track whatever language accepted by the single track Turing machine or basic Turing machine, it is also same language is also accepted by the multi-track Turing machine. For that we say both are the same power. Here there is an example, multiplication of two unary number by using single tape Turing machine. So here two unary number 3 into 2, we converted 3 into 3 ones and 2 into 2 ones, and it is separated by a 0. So our basic aim is to copy first the head is point to the first one, and I will make it blank. It will be make it blank. Then we'll go, when I got another one, I will go to right. Again another one, I will go to right. Then 0, go to right. Again when I got a 1, I will make it x and go to right and make it 1. When a 0, make it right and again it 1. Again like that, again read this one and make it x and go to right, make it 1. It means copy. Copy these 2 into this blank. Again I go to and make it 1. X to 1, again 1. Like that, again go here and again 1 is blank. Then again same process will be continue up to when all the first ones are blank. So like that it will be continue. This step is explained here. Here n is the 3 and m is 2. In this Turing machine it is explained that n is 3 and m is equal to 2, and this m and n is separated by a n as m is separated by 0. So this is explained here. First I make it blank, then after that we will go right, and this will be described in the transition diagram. If I got 1 first, then we will go, then write the blank and go to right. Again I got 1, then write 1 and go to right, like that. Here when I got 1, write 1, make it blank and go to right. If I got 1, make it 1, write 1 and go to right. Again I got 1, make it 1, write 1 and go to right, like that. If I got 0, write it 0 and go to right, like that it is written. If I got 0, write it at 0, write 0 and go to right, like that this diagram will be described, and the same method will be continue as the up to halt. All the ones are copied. Then example of problem of multi-track Turing machine. So here multiplication of two integer using multi-track Turing machine, n into m, and the algorithm is like that: place n in track 1, place m in track 2. It means n is the number 6 and m is the n is equal to 6, m is equal to 4. So we place 6 in track 1 and track 2 is 4, and this is the resultant track. T3 is the resultant track. T3 is our resultant track. So next step is third step is if T2 is equal to 0, result in T3. It means when T2 is 0, here T2 is 0 and the result is 24. How it is calculated? I will explain step by step. So step 5, T3 is equal to T3 plus 2 T1, and we will reduce T2 as 1. When T2 is equal to 0, then stop. For example, our aim is we will add these two. 6 plus 0 is equal to 6 and reduce T2. T2 means reduce T2. T2 means I will reduce 4 to 3. Again 6 add 12, 6 add 12, and again it is reduced to 2. Again 6 12 is 18, reduced to 2 to 1, and finally 6 18 24 and reduce 1 to 0. When T2 0, T1 is answer. That is written as in the first track 640 it, and 640 and 640 right. Then next is 640 636. 636, then go to right. Next is 6 to 12. 636 is the input, 6312 is the output, and go to right. Like that, finally, when t to 0, it is the write the answer. Then we go for multi-tape Turing machine. In single tape Turing machine, it has single tape up to like that. It is a finite control unit which read one cell at a time and up to end, and we will move left to right. But in the multi-tape Turing machine, it has multiple tape with multiple head. How much tape? It is that much head. Here 3 tape, 1, 2, 3 tape. Also the head is pointing the different tape. But one thing is, it has same power as basic Turing machine or single tape Turing machine. Why? Because what language solved by the basic Turing machine, same language is solved by the multi-tape Turing machine. How? Suppose here it is written as 0 1 0 1 0, then blank. This U is blank symbol, infinite blank symbol. And second tape it is written as A and blank symbol, third A, B A and some blank symbol, infinite tape. So that also we represent in the single tape Turing machine. How? Suppose here the one position is the position of head is in the 1 in the first tape. So we write all the symbols in the first 0 1 0 1 0 0 1 0 1 0. Then we make a marker, that is end, and again second tape symbol, then there is a marker, then again third tape symbol in a single tape. So then it is infinite tape, so we can keep infinite symbols. So here where the head position, I will give a marker here. This is the head position of tape 1, and this is the head position of tape 2, and this is the head position of tape 3. Like that we will simulate the basic Turing machine or single tape Turing machine with multi-tape Turing machine, and whatever language solved by the single tape Turing machine, also same power as the multi-tape Turing machine also solve that particular language. Then here there is an example, K-tape with solve the palindrome. Here palindrome is rotor, ROTOR is given. So here we will copy the rotor to the second tape. Here R is copied, O is copied, then T is copied, then O is copied, then R is copied. So it is 2 into order of n. Then what to do? Again the first tape will move left to position the first position. Again if it is matches, then we will make a cross in the second tape. If it is matches, the two symbol are matches, then we make a cross in the second tape. R is matches to R, then we will make a cross. Then O is matches to O, make a cross. Then T is matches to T, then make a cross. Then O is matches to O, then make a cross. Then R is matches to R, make a cross. So it is order of n. It means first is 2 times order of n, then order of n, then 2 times order of n, checking 2 times order of n. So the complexity is order of n. If it is done in single tape Turing machine, then it is order of n square. If you do in the single tape Turing machine, then it is order of, because every time you make right, go to right and make it cross, again left, make it cross, again make cross, like that. So it is order of n square. So next we go to non-deterministic Turing machine. So non-deterministic Turing machine is a theoretical model of computation that extends the capability of deterministic Turing machine by following multiple possible transactions. Like NFA, it has multiple transactions. Same symbol, we can go left or right, and also branching also. If multiple transactions, then branching, and we also read the multiple transaction, branching, and also simulation, and also discuss the computational power and also applications. Here multiple transitions. A DTM has a single transition. Either we read a symbol, here we read a symbol 1, suppose symbol is 1 or A, this is the read write ahead, and read a symbol, either make it X, go to left 1, either left or right. But in the NDTM, non-deterministic Turing machine, you can go left or you can multiple transitions from a state. So for multiple transition, there is a branching concept arises. Due to multiple transition, a state gives rise to branching path of computation. At each non-deterministic choice point, the machine can follow different path. Whether we can go left side or right side, that is the two paths, potentially exploring the multiple possibilities simultaneously. Simulation. So if it is a multiple transition, but one of the path will be accept this, whatever the basic Turing machine accept or DTM accept, also that language, also same language, also non-deterministic Turing machine also accept, because one of the path will choose that in the different path will choose one of the path that will be accepted by the NDTM. So for that we will say the computational power of the basic Turing machine or a DTM will be same as the NDTM. But if it is a multiple path like tree structure, multiple path, any of path you go, you can choose your path and finally you accept the language. So it is the 2 to the power n time, it will take 2 to the power n time. So in the case of simulation, despite the non-deterministic nature, NDTM can be simulated by the deterministic Turing machine. This is done by considering all the possible paths. We draw all the possible paths of the NDTM in parallel and simulating them sequentially one by one. So application, non-deterministic Turing machine are primarily used as a theoretical tool. It is a theoretical tool in the study of computability and complexity theory. So here is the NDTM. All of you know that it has the Turing machine has 7 tuples. One is the Q is the set of states, and sigma is the input alphabet, tau is the tape alphabet, and one thing difference is here. It is the power set. But in power set of Q into tau, left or right, the power set, because there is many possibilities. For that we can take power set of Q into tau, left or right, and Q0 is the start state, and Q accept is the acceptance state, and Q reject is the rejectance state. Here is the example of NDTM. Here delta, here is the example, whether this A, B, B, A is accepted by the NDTM or not. So we will check here Q0A, there is multiple path, either it can go Q0BR, Q0BR or Q or you can go here Q1, we will read the Q1 by using you will write the B and R here. Either this path we can choose or this path we can choose by putting the A. Though your input symbol is here, here is the A, here is the two paths. So the branching. So next we will choose this path. Any of the path will be choose. Suppose we choose this path, this is the acceptance set. Then again A will choose this path first, and again A this path first. Then next, then B. When you read B, then go to here. And how many B you read? 1B, 2B, then next B, here we will move. Then Q3A, if I read A, then make it blank and go to Q4. And then again A. When I read A, then make it blank and go to acceptance state, which is QF or Q5. So this is the quiz questions, some of the quiz questions and the question. Thank you.